Rotameters, they are very simple flow measurement meters. They have to be mounted in a vertical manner like that, and the idea is that the flow pushes this little thing upwards and the gravity pushes it downwards. And since it gets wider here, the gravity will always push it downwards with the same force, but the force applied by the flow is lower on the wide section here than on the narrow section. So the little object here will stop at the position where associated with that specific flow. It's commonly used to provide a cost-effective local indication of small liquid and gas flows. Local indication means that you go up to the instrument and read it directly through the transparent glass here. And they are used for small flows. You cannot use it for like in a waterfall or something like that. You need to be careful when using it because you need to use fluids that will pass the light through. You cannot use it for totally black fluids, for example, and they can vary in size to up to 8 centimeters, which will indicate the flow rate. Of course, you can make a reading. You can use elements to read where this little object is, but they are mainly used for direct reading on site. Turbine meters, very popular. For example, every gas pump around the nation have turbine meters to measure the amount of flow that runs from the pump into the tank. And they are used for water, petroleum, chemical industries. They need a bit of flow in order to measure accurately, and because there are things that will slow down the rotor. So actually, if you have a very, very slow flow rate, then actually you may end up with a turbine not rotating at all. And then you have every measurement principle where you have moving parts will have a reduced lifetime. So, for example, if you have dirty fluids and such, that will reduce the bearings, the lifetime of the bearings, and also abrupt transitions from slow to fast flow will mechanically stress the flow meter. So they can be used basically for clean fluids where you have an expected high velocity of the fluid, for example in a petrol pump. But then again, they are very cost effective. So you only need some tool to measure the rotation of the turbine inside there. One simple principle is the Vortex principle, where you have a so-called blunt body, and when the flow passes through or via that, vortices will form on either side of behind the object. The thing is that the distance between two such vortices will be constant. So if the flow rate goes up, the distance will still be the same between two vortices, and therefore by counting the vortices you can actually count the flow rate. You can use that to calculate the flow rate. So the idea is that you need some tool to find the vortices. And one idea is that if you have the obstruction here, you can have a kind of a rudder in just behind of it, and that rudder will go back and forth actually into the vortices, because the vortices, they have higher velocity and thus they have lower pressure. So the rudder here will go into the vortices, and go back and forth, and you can count the movement of the rudder. In the film from Andressen-Hauser, it looks like the rudder is going away from the vortices, but that's wrong actually. So you have to count the number of vortices per second and use that to calculate the flow rate. It's and the principle here is very much like if you have a flagpole, you see the flag behind it will follow the vortices that form behind the flagpole. Independent of density, temperature, and pressure, flow meters may turn off if you have non-linear or flow or very low flow rate. So you need again a bit higher flow rate than other measurement principles. You can apply it to corrosive liquids and fluids with particles, and piping vibration may cause unreliable measurements, but as you will see in the film from Andressen-Hauser, they have found a solution for just that.